Hello everyone, welcome to our discussion of section 3.3 where we will be talking about derivatives of logarithmic functions and exponential functions. As you recall, in section 3.2 we talked about, or we did a quick review of logarithmic and exponential functions because we've seen those before in pre-calculus. This time we will talk about their derivatives, which have their own particular techniques in addition to the derivatives of other functions we've learned so far. So suppose we want to take the derivative of some function, some logarithmic function. Let's take a basic, easiest one, such as this, log of x to some base a. Then this derivative, or derivative of this function with respect to x, would be equal to the reciprocal of x, or whatever you see here. This could be anything. It's the reciprocal of that entity or the argument of the log function, in this case 1 over x, times log of e to base a. So let us box this. Now, this formula has an equivalent form. So let's say or, and let's just quickly, because it's so easy, let's derive an equivalent form of the same form, derivative formula. So we know that the log of any value can be written in terms of using the change of base formula, right? We talked about change of base formula in the previous section. So using that, we know that we can write this piece, or log of e to base a, as natural log of e over natural log of a. Okay? That just applying the change of base formula. And let me actually write that down. We know that this is the case for this piece only using the change of base formula. Change of base formula. At the same time, when we talked about properties of logs and natural logs, you remember that the natural log of e simplifies to 1, right? Natural log of e is just 1. So let's say that we also know that natural log of e is equal to 1. So then we can replace that log of e to base a with 1 over natural log of a. Thus log of e to base a is equal to 1 over natural log of a. Okay? So knowing that, then we can replace log of e to base a with 1 over natural log of a, or 1 over x times natural log of a, as an equivalent form of this derivative. Okay? So thus, or therefore, we can rewrite that formula, that derivative formula, in this form: d dx of log of x to some base a is equal to, just substitute for this piece with that, it'll be 1 over x times natural log of a. Like that. Okay? So either this, you can use either this form or this form. So these are interchangeable. They are the same formulas expressed differently. Okay. So let's continue with more formulas here. Now, if you want to take the the derivative of natural log of x, or let's say d dx of natural log of x, that would be equal to 1 over x. Okay, that makes sense because natural log of x has base e, and natural log of e, which is the base, would be 1. So 1 times x is this. So this is, again, simplification. This is a simplification of that formula if you have natural log of x rather than log of x to some other base than e. So natural log of x has base e, which simplifies this natural log of a to just 1, which we end up, for this reason, we end up with 1 over x. Of course, the chain rule that we've already learned about applies here as well. So for example, so suppose we have a function of u, a variable u that is like that, natural log of u, and we have, let's say, g of u is equal to, or let's see, let's say gu, or u is a function of x. Let's just say it that way. I think that's even better. So let's just say, and u, this variable u, is a function of x, some variable x, right? Therefore, then we can say the derivative of natural log of u with respect to x, the derivative of natural log of u with respect to x would be equal to 1 over u, 1 over this u, times du dx, okay, by the chain rule. So let's box this and say by the chain rule, okay. We'll do plenty of examples of this here in the video, as well as when we work on the worksheets, and you'll see exactly how these formulas are applied. So let's look at another formula for finding the derivatives. So I'm going to try to put a couple of more formulas here and here. So d dx of natural log of g of x, right? That is equal to, let's see, g prime gx over gx. So it's the reciprocal of this function times the derivative of this. Again, this is the chain rule. So this is once again a chain rule. Applying it. So this was u is some function in terms of x, and that's 1 reciprocal of u times the derivative of u with respect to x. Here, whatever that, take the reciprocal of this whole function, which would be u in that case. So in this case, g of x, take the reciprocal of this times the derivative of g of x, which is that g prime x. So this is, again, the chain rule. We're applying the chain rule here and here. And finally, one of the useful but easy to remember formulas is this one. the derivative of natural log of absolute value of x. So take a look at this combination. It's the natural log of an absolute value. Then this would be 1 over x. Okay. So this is a very, very important note. It's sometimes, occasionally you come across absolute value functions, and there is this technique is very, very useful in helping us find the derivative of absolute value functions. So important note. So to find the derivative of just an absolute value function, we're not talking about, see, this one combines the absolute value with the natural log function. So 1 over whatever inside, right, inside the absolute value. Of course, the chain rule applies there too. But what if we just have an absolute value function with no natural log involved, or no log function involved at all? This important note is about finding the derivative of such functions. So to find the derivative of just and let me in parentheses say with no log or natural log involved. Okay, without any log or natural log, such as this, f of x equals absolute value of x minus a So the first step we do is to rewrite this as in a radical form. The first step is to write this same function, absolute value function, as f of x equals a square root of x minus a squared. Okay, so that absolute value function is equivalent to this radical function or a square root function. Okay, these two are equivalent, identical. Okay, but written in a different way. So now and then using the exponential or power form of this, which has rational exponent as opposed to this. So then using the form with a rational exponent. So notice that this is all, we're just writing this original expression, absolute value expression, in different forms. We wrote it in this form, now we're going to rewrite it in a different form, which is the same thing as before. Which is that before finding the derivative, so even though the main focus of this section is just derivative of log or natural log functions. I've seen examples that in this section that this might be useful when we get to them, or this is useful when we get to them. But for now, just have this as an important note in your notebook or in these lecture notes. We will refer to this again in this course. But this is a very useful thing to remember. And I'm going to box it with my highlighter like that. Okay, we will refer back to this. So these were a few techniques for finding the derivatives of logarithmic functions. Now let's give a few techniques, very few, for finding the derivatives of exponential functions. Suppose we start with a function like this. Let's take a basic exponential function, some base to some power x, right? And knowing that a, or the base, must be some positive value, some non-zero positive value. Then, if we want to take the derivative of such exponential function, the most basic exponential function, right? A to some x power, that is equal to the exponential function, a to the x, whatever it was, times natural log of the base. Like that. And of course, this has its equivalent using the chain rule, right? So suppose this was not x, but it was this power was some function of x. Then we could apply the chain rule. So let's also mention that. And also by the chain rule, we have, say, the derivative of, instead of x, we're going to put u being some function of x. Okay, so then we take that whole exponential function, we multiply it by the natural log of the base, we multiply that by the derivative of function u with respect to x, or du dx. So this piece is by the chain rule. Okay, so let's also box this. And this is by the chain rule. Now here's my favorite derivative of all. One of the most important exponential functions is in all of mathematics has a very easy to remember derivative. And what is that, you might ask? Here it is. d dx, or the derivative of function e to the x, guess what is this equal to? E to the x. Okay, so that is the derivative of e to the x is equal to e to the x. It's neat, isn't it? And of course, this one has the chain rule equivalent of itself. So let's also mention that. By the chain rule, if that x is some function in terms of x, we can apply the chain rule. So we say d dx of e to the u function. Then we have e to the u, e or e to u power times du dx by the chain rule. And this also box this. Okay, like that. One other note, I mean, I already mentioned one, in addition to these formulas that we're introducing for finding the derivatives of exponential functions and logarithmic functions, I introduced this note that helps us find the derivative of an absolute value function. So let's remember where that is. This is section 3.3. There's also another note that I wanted to mention. So this is note, or another, let's say, important note. Okay, so we may come across complicated functions that involve products, quotients, and powers. In such cases, let's remember this technique also, that we can take the logarithms of both sides of the equation to simplify it. For example, you can, if you have a quotient, you remember the property of logarithms, right? If you take the logarithm of a quotient, you can convert that quotient to the subtraction between two separate terms. So we can use techniques like that to change the expression such that it's easier to find the derivative for it. Okay, so that's one of the useful techniques. So actually, let's do an example on this one. So here is one example where we want to differentiate y equals x to 3/4 power times square root of x squared plus 1 divided by 3x plus 2 to 5th power. Okay, this is rather complicated expression. You have a power function here, you have a square root function, you have another binomial to 5th power in the denominator. So it's not an easy expression to find the derivative for. But now let's take the derivative of both sides. Okay, so we want to say natural log of y is equal to natural log of the right-hand side, right? Natural log of x to the 3/4 power. In fact, I really stole this particular example from your book. Your book has solved this example fully in this section 3.3, but it was such a good example that I wanted to talk about it too during this video, because usually or most often I use examples that are not solved in the book. So you have the examples solved in the book, then you have these examples, so you have more examples to look at. But in this case, I made an exception because it's such a good example to go over using this technique. So we take the natural log of both sides in this case, and natural log of x to the 3/4 times square root of x squared plus 1 divided by 3x plus 2 to the 5th power, like that. Okay. So now we know that we can write this right-hand side in terms of the difference between these expressions, right? Using the law properties of logarithms that we've already learned about. So natural log of y is equal to natural log of x to 3/4 power times square root of x squared plus 1 minus natural log of all of that, 3x plus 2 to the 5th power. Right? So, okay, we can do more to simplify the right-hand side. So what can we do? We can say that this x to the 3/4 power is being multiplied by that, so we can, again, using the properties of logarithms, we can change this to addition of two terms. Go from product to addition using the property of logarithmic expression. So let's do that. So natural log of x to 3/4 power plus natural log of square root of x squared plus 1 minus that whole thing. So I'm doing this step by step just so everybody can keep track of this, but you don't have to. You can jump ahead, right? For example, I'm sure if not all of you, most of you probably saw that you could bring this 5 down and in front using the properties of logarithms, but I'm just doing this step by step. So hopefully that helps. Rather than be more boring, hopefully it'll be more helpful. Okay, so now let's simplify. Notice we have not taken the derivative. All we're doing is we're making use of the properties we know to make our expression simpler. Okay, so that's a very useful way of approaching approaching to find the derivative of complicated expressions. So let's bring this 3/4 down and in front. 3/4 times natural log of x. This is, of course, this square root of x squared plus 1 is really x squared plus 1 to 1/2 power, right? Written in power form. So let's convert that. So we can write plus 1/2 natural log of x squared plus 1 minus, of course, 5 times natural log of 3x plus 2. Okay, all using the properties of logarithms. Now we can find the derivative of this expression because we've simplified it as we can, as much as possible. So natural log of y has an easy derivative, right? It's just 1 over y, and y is this y. This y was a function of x, right? So we have to use the chain rule here. If this was x, if this was natural log of x, I would stop there. I would say 1 over x equals. But y, this is not x. So this is y, which is a function of x. So we need to apply the chain rule. Dy times dy dx on the left equals, so this is 3/4 times 1 over x, right? We don't have to use the chain rule here because x is just x. This is not a function of another variable. This is just a variable. So 1 over x. That's the derivative of natural log of x, as we just learned. And plus 1 over 2 times 1 over this entire thing, x squared plus 1. Now that expression is a function of x, so we need to use the chain rule. What's the derivative of this inside the parentheses? It's 2x, right? Just 2x minus, now this is again 5 minus 5 times 1 over 3x plus 2, or minus 5 over 3x plus 2. This is, of course, this expression is a function of x. So we have to use the chain rule, times 3, right? Times 3. Okay, so let's simplify again this one a little more. So we have dy on the left. We have dy over dx equals, if we multiply both sides by y, right? This multiply both sides of this equation by y. The y cancels out on this side. We have dy dx. And then on the other side, we have y times all of that, whatever we have. But let's simplify it. So 3 over 4x plus 2x, actually, right? The 2 and the 2 cancel out. We end up with x over x squared plus 1 minus 5 times 3 is 15 divided by 3x plus 2. Like that. Okay? But now you might say, well, what is this y there? Well, we know what y is, right? Y is equal to that. Y is equal to all of that. So let's replace the y in the derivative with its equivalent that was the original function. But we already know what y is, right? So let's plug in. We end up with dy dx equals all of that expression that we had, x to 3 excuse me, x to 3/4 power times square root of x squared plus 1 divided by 3x plus 2 to 5th power. That's y. This whole thing is y times all of what we had times 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. Are we done? Yes, we are now done. Okay, so that is the full derivative of that expression. So you see why this technique is so important. We had a complicated quotient in the beginning, and we were able to simplify it by taking the natural log of both sides. You can do the same thing with logs, but natural logs are also useful too. Okay. So let's do more examples, right? We've seen enough formulas. Now let's apply them. Now would be, because we've spent some time now, we've done a few examples, like 2-3 examples so far. So from this point forward, use that knowledge to do your own work on your own scratch paper. And then, so what I mean is pause the video, do your work, and then come back to the video. Okay, I highly encourage you to do that. That's the only way to get you used to these techniques. Okay, so we want to find the derivative of, so let's differentiate the following. So suppose, let's call this A. Example A, suppose we have f of x equals x natural log of x minus x. So here we can use the product rule, right? So f prime of x, the derivative of x is just 1 times natural log of x plus, I'm just applying the product rule, and then the derivative of natural log of x is 1 over x times x, right? So 1 over x times x. Of course, the derivative of minus x is just minus 1. So let's simplify. F prime x is equal to natural log of x plus x over x is 1. 1 minus 1, right? Let's just say plus 1 minus 1, and that's just 0. So we end up with f prime of x is equal to natural log of x. Okay. So I hope you pause the video because we're building on, these are easy examples and we're building on these. So the examples become a little more complicated as we move forward, but I hope you're building your skills up by pausing the video on these easy ones especially and trying to get these answers on your own. And if not, no harm done, right? You're just watching this video. So you can learn, you can only learn from it. All right, so this one, let's say if we have a function such as this, f of x equals natural log of sine squared x. So go ahead, pause the video, and once you're finished, you're then come back to the video and see, compare your solution with mine. Okay, so I'm assuming you've done that, and now you're back. So f prime of x, this is a natural log function. So we take the reciprocal, to find the derivative, we take the reciprocal of the argument, whatever it is, in this case, sine squared of x. But the argument of this natural log function itself is a function, right? Sine squared of x, or sine of x, is a function itself. So we have to apply the chain rule. So we take the derivative of this function. But let's also rewrite it. So d dx of, I want to rewrite this with the power on the outside because it's very helpful to have the powers on the outside when we take the derivatives. So d dx of sine of x, the 2 power on the outside squared. Okay, so now f prime of x equals 1 over sine squared x times, what's the derivative of this? 2 in front, right? 2 comes in front, times sine of x to power 1. We reduce this power by 1, right? So times 2 sine of x, the power is reduced by 1, so I'm not going to put anything here, times, by the chain rule, the derivative of sine of x, which is cosine of x, like that. Or you could have just done this. I did it, I combined a couple of steps here. You could have said 2 times sine of x, and then in parentheses cosine of x. You could do that too, but eventually you end up with this. Can we leave it like this? No, please don't do that, because we can simplify this, right? If you left it like this, it's not inaccurate, but the derivative is not complete because we haven't simplified. So let's simplify, because we have a sine squared x here and a sine x here. So this cancels out with 1 of that. So we end up with, what do we end up with? We end up with 2. This sine of x cancels with 1 of this, because this is sine squared x, which means sine x times sine x, right? So 1 of that cancels with this. We end up with just 1 sine of x in the denominator and cosine of x, of course. But from trigonometry or math 127, you all remember that cosine x over sine of x is, cosine of x divided by sine of x is equal to cotangent of x, right? So let's write that down also. So we have f prime of x equals 2 cotangent of x. Okay. Let's do the next example. So I hope what I have here matches what you wrote down on your own scratch paper. If not, I hope that at least you took it this far. Okay, so we have another one, y equals 1 over natural log of x. So this is a quotient. It's a very, very simple quotient, but we can apply the rule for finding the derivatives of quotients, right? Do you remember how it works? So we start, so this is dy dx. We take the derivative of this, multiply by what's in the denominator. So the derivative of 1 is just 0. The derivative of any constant is 0, right? Times natural log of x. Then we subtract the derivative of the denominator, which would be 1 over x in this case, times whatever we have in the numerator. All of that, of course, divided by the denominator squared. So natural log of x squared. Okay, so let's simplify this. That's, of course, 0. So we end up with y prime equals negative 1 over x. That's just that. Divided by natural log of x squared. And then we can simplify this a little bit because this is a complex fraction. So we write y prime is equal to minus 1 over x times natural log of x squared. Like that. So I'm not sure if you, I hope this is not confusing to go from this complex fraction to this, but just in case some of you might have questions about that, let me remind you that that just goes back to, I'm just going to use a piece of scratch paper and explain that a little bit, just in case some of you might have questions about it. So we are at this point, right? Minus 1 over x divided by all of this. Now, this is a complex fraction. Complex fractions, the easiest way to simplify them is, first of all, give this one its denominator. The denominator of this one is 1, right? Then the easiest and most efficient way of simplifying complex fractions is multiply the farthest terms. In this case, minus 1 and 1 are the farthest away from each other, right? Minus 1 and 1 are farthest away from each other. So minus 1 times 1, and put that in the numerator. And then multiply the nearest terms, the x times natural log of x squared, and put them in the denominator. And you're done, right? All you have to do, just simplify. Minus 1 divided by x times natural log of x squared. This expression, which is what we have here. Okay, so that's what I did going from here to there. All right. So let's do another example. Suppose we have a function that is log of x times e to the x to base 5. Okay, so let's find the derivative of this. So we have f prime of x equals, let me bring that in the beginning, what we talked about here. So remember this one, this formula, log of some value, some x to some base is 1 over x times natural log of this, right here, actually. right here, sorry. So that was one form, but I can tell you, and we mentioned that these two forms are equivalent, remember, on the first page? I can tell you that the most popular one is this one, this formula, not the other one. So using the natural log of A. But sometimes the other one is used too, but this is more popular. So one, take the reciprocal of that argument, in this case x, and in the denominator we multiply x by natural log of that base. So let's do that here. So we take 1 over all of that, and of course we have to do the chain rule, right? Look at this. This is a whole function, so we have to do chain rule after that. But for now, 1 over all of that times 1 over natural log of this base, which is 5 in this case. Now by the chain rule, times the derivative of all of this by the chain rule. So x, this is just the product rule for finding derivatives, remember? So derivative of x is 1 times the other term, e to the x, plus the derivative of e to the x, which is e to the x, times x. Times x. Okay? So let's simplify here. We have f prime of x equals, let's combine these, we get, so we have 1 over natural x to the x times e to the x times natural log of 5, right, multiplying that, times, let's simplify this, e to the x plus x times e to the x. Now we can, of course, combine this with that. So e to the x plus x times e to the x, that's just times 1, divided by, actually we can simplify it even after that. So I just saw that. So x times e to the x, natural log of 5. Okay, so in the numerator we can factor out e to the x, right? Let's do that. Times 1 plus x, and then in the denominator we have that, right, e to the x. So these two cancel out. We end up with f prime of x equals 1 plus x divided by x times natural log of 5. Like that. Okay? All right, so let's do another example. Suppose we want to find the derivative of this expression, natural log of absolute value of cosine times cosine of natural log of x. So here, natural log of x is the argument of the cosine function. All right, so we have y prime equals 1 over that whole thing, right? 1 over this whole thing, cosine of natural log of x, times, by the chain rule, the derivative of whatever we have on the inside. The derivative of that, this is cosine of natural log of x, so the derivative of that is minus sine of natural log of x, of course, times the derivative, again, by the chain rule, times the derivative of what's inside this parentheses, which would be 1 over x, right? The derivative of natural log of x is 1 over x. Okay, so let's simplify. We have y prime equals, let's see, we have minus sine of, so this x times that, so we have minus sine of natural log of x divided by x times that, x times cosine of natural log of x. Okay, let's see. So what would you do at this point? Would you stop? Would you stop at this point? Take a good look at this. What would you do? Would you simplify this with this? Could you do that? Could you cancel natural log of x and natural log of x? No, you could not. I hope you can see why not, right? Because natural log of x is not being multiplied by sine. This is not a multiplication. This is not a multiplication operation. Natural log of x is the argument of sine of x. So here we have a composition of functions. And natural log of x cannot be canceled with this natural log of x because it's part of the argument of the sine of x, and here it's part of the argument of cosine of x. So what can we do then? Well, let me, instead of jumping to the next step right away, let me give you a hint. So suppose if I write this a different way, I'm going to write it as minus 1 over x, right? Minus 1 over, I can do that, times sine of natural log of x divided by cosine of natural log of x. Remember, you cannot cancel natural log of x terms here because they are not being multiplied by sine of x. They are part of the argument of sine of x. So they stay. So what can you do? To simplify this, what else can you do? Well, from trigonometry, we know that sine of x divided by cosine of x is tangent of x, right? So we can do that. We can say y prime is equal to minus 1 over x times tangent of natural log of x. Okay, so we can do that, or then we can make it more compact by saying minus tangent of natural log of x divided by x. Okay, like that. I hope this made sense. All right, so let's do another example. Suppose we want to find the derivative of this expression, natural log of 1 plus e to the x squared. Okay. All right, so we can apply the power rule here, bring this 2 in front, so y prime is equal to 2 multiplied by all of that and reduce the power by 1. Like that. So 2 minus 1 is just 1, which I'm not going to write. And then by the chain rule, we need to multiply all of this by the derivative of this. So the derivative of this is 1 over all of this. Like that. And then times, again, by the chain rule, the derivative of inside the parentheses, which is e to the x. Okay, so we have then y prime is equal to 2 times e to the x, this 2, times e to the x, times natural log of 1 plus e to the x, divided by 1 plus e to the x. Okay, so let's do another example. Suppose we want to find the derivative of y equals log 2 base 2 or log of e to minus x power cosine of pi x 2 base 2. Okay? So what would you do here? What would you do? Think about it. And I hope you've been pausing the video at the beginning of every example to do your own work before you see these solutions. But what would you do at this point? Well, we've learned about properties of logarithms, right? So if you apply that, what happens to this? So what we'll get, so apply those. We have a multiplication here. We can change this to addition. So by that, the main objective, of course, is to break this expression up, to break it up into two smaller expressions, which would be easier to find the derivatives for. Okay, so let's do that. Log of e2 minus x, 2 base 2, plus log of cosine of pi x, 2 base 2. Right? So we created two smaller terms from this larger term. Now we can take the derivative of this. So we have 1 over all of that, 1 over e2 minus x, times the derivative of this expression by the chain rule. Of course, that's minus. Minus comes from this power. Minus times e to minus x power. We have an e here. We can say log of e to base power, to base 2. So log of e to base 2. How did we do that? This is the formula. I applied this formula. The derivative of that, log of some expression to base a, is 1 over that. We already did that. 1 over e to the minus x. We already did that. Times log of e to base a. Okay, so I'm using this very first formula we talked about. That's that. And this is, of course, comes in because of the chain rule. 1 over that times the derivative of that, because that's its own function, times the log e to base 2. And then this one. So again, 1 over all of that. So 1 over cosine of pi x times the derivative of this, which would be minus sine pi of pi x by the chain rule times pi, right? Pi x has derivative pi. So these are a series of functions. You have the log function, then you have the cosine function, then you have the pi x function. So all of these, you have, by the chain rule, we have to take the derivative of. Of course, all of that, remember these? This expression, 1 over x times log e to base a, or 1 over x times natural log of a, natural log of this base. So we can do that, times natural log of 2. 1 over natural log of 2, right? So 1 over x times natural log of the base in the denominator. So I'm applying. So in this expression, in this derivative, I used both this one. I used both this formula and this formula. They're the same. So times 1 over natural log of 2. Okay? Let's simplify. So we have y prime equals, well, look at that. This one and this one cancel out. We only end up with minus log e to base 2. So minus log e to base 2 plus no, we have a minus here. So that'll change this plus to minus again. That's the only minus. It'll change this to positive to minus. Is there anything else we can simplify here? Let's see. Pi times Yes, there is. We can convert these to tangent, right? But let's do it like this. So minus pi over natural log of 2 times sine of pi x divided by cosine of pi x, right? Now, from trigonometry, Math 127, we learned that these two, sine of something divided by the cosine of that same something, equals tangent of that, right? So let's do that. So we end up with y prime equals minus log of e to base 2 minus pi over natural log of 2 times, actually let me write it down, write it up here, tangent of pi x. Okay, tangent pi x times that times pi over natural log of 2. So that would be the final result of this derivative. Okay, so we have come to the conclusion of another section here. Please practice with these derivative techniques we've been learning for the past few sections in Chapter 3 and before that in Chapter 2. The only way to remember them is just look back at them, practice with them, go over the same examples that you see in the book or you see in these lecture notes. You can download these lecture notes anytime, as you know, so download them and without looking at the solutions, review and redo these problems just to remember these techniques, because we will be using these again and again throughout this course. So thank you for watching this video lesson until the end. For now, have a nice day, and I'll see you again next time.